This is a lecture on basic statistics and data analysis, in which we will refresh some of the concepts that you already might be very familiar with. Then, through two case studies, we will look at how a good analysis leads to valid insights and great visualizations.
Okay, so today's lecture is about data analysis and insight finding. So it's not a very detailed lecture on data analysis, because we don't have, if I have to do data analysis itself, as some kind of a data science type of a lecture, it would take me 2-3 lectures to cover it. So I'm kind of going to compress a lot of stuff. Some of it might be familiar to the MDes students who have done DRM. Design research methods, quantitative methods especially. But for others, the level of analysis that I'm going to talking about is not at a very high level. Therefore, many would be very easy to understand, as well as kind of intuitive or commonsensical in nature. Okay. So let's get started with the. Okay, so this is by no means a technical lecture either on statistics and data analysis. So that's the first disclaimer. I will, however, talk about the essentials, fallacies, paradoxes and curiosities in data collection and analysis. Okay. So this is kind of the follow-up lecture to data. Okay. So ideally I would do the data lecture first, follow it up with this one, and then go into the design visualization design lecture. But because I wanted to do both data as well as the design on the same day, so that you can use it in your assignments, I kind of reshuffle the order. Okay. So that would be the right order to look at it. Okay. So think of it as a continuation of the data lecture that we saw. Okay. And why good data and sound analysis matter a great deal in finding valid insights and good visualizations. Okay. So that's basically the objectives of this talk. So I'm going to start as usual with a story. So there was a World War II classified program called the SRG that worked out of New York, from Manhattan, not Manhattan, assembled the might of the American statisticians to the war effort, something like a Manhattan Project, except the weapons being developed were equations and not explosives. So there were a bunch of people who went on to become luminaries in their own fields, such as, say, Molster, who was the founder of the Harvard Statistics Department. He was not at the time, because he was a young chap like you guys, right, trying to help the country in the war effort. Then Jimmy Savage, he would later on go on to find this field of Bayesian statistics. Again, went on to work with the university. Then Weiner, who was an MIT mathematician and the creator of cybernetics. Milton Friedman, who was the most well known of all of that, was an economist, and he was a future Nobel Prize winner in economics. Okay, so this is the bunch of people who were working for SRG at the point of time. Okay, so what was they supposed to do? I mean, what is a bunch of these nerds going to do in a war effort, right? Which is like this very macho thing, right? So their problem or their brief was, how do we optimize? Okay, so the winners in any war are usually the side that gets 5% fewer of their planes shot down, or use 5% less fuel, or get 5% more nutrition to their infantry at 95% of the cost. Where can we shave off these small costs, right, so that it makes a difference, right? Because in an equally matched war, which is what it is, the current Ukraine war is turning out to be, right? Initially, pundits predicted that these two countries are vastly outmatched, and Russian power is so much that they're going to overwhelm it. The war is going to be finished within a few days, and that nothing of that sort. So we are close to 120, 130 days now, and still the war is going on, and it's going to be an impasse with no clear winner, and quite likely that Ukraine might come out better at the end of the whole thing, right? So a lot of calculations went wrong. One of the calculations that went wrong for Russia especially was how they did not optimize it, right? They kind of thought that, they kind of banked on this overwhelming force in the beginning that would account for a lot of their problems, right? That many of us, many people thought that they would not come to, we would not come to a point where these problems that the Russians had would matter, But then when the war stretched, it's all about how do you optimize on many things, right? And we are learning through a good example of how optimization is playing a big part in a war, and even very unequal sides can kind of eventually present a war that appears very equal at the end. Okay, so there was this problem that was presented to this group. This is one of the typical problems that they would face every day. Okay, so how to armor the plane? Okay, so this is the data that they got collected from the field, which points out where the bullets or where the holes are on a plane. Okay, so I think this plane is a very specific type of a plane. For those people who are interested in what it is called the Republic P-47 Thunderbolt, one of the largest and the heaviest fighter planes in the history, and it was powered by a single 4-stroke internal combustion engine, and it was built between 41 and 45, 1941 and 45, and it was heavily armed with guns and stuff like that. Okay, machine guns, four machine guns per wing, and when it was fully loaded, it weighed up to 8 tons. And the fighter bomber ground attack roles could carry 5-inch rockets or a significant bomb load of 250,000 pounds, 2,500 pounds, sorry, 250. Okay, so this was the main warplane of the Allies. The Allies are essentially the US and most of the good guys in the Europe, right? So of course they lost a lot of planes. There were also planes that returned with suffering some damage, right? So they looked at all the planes that got back and then counted the holes and where it was. Okay, and then they counted many planes, and then on average, for whatever reason, they decided to categorize it. They divided the plane into these 4 parts: engine, fuselage, fuel system, and rest of the plane, and then meticulously counted each hole, and then averaged it across all the planes, and then came up with this number. Okay, as you can see that there is a disparity of it, even though it kind of appears. So the problem that was presented to the SRG was that now we have to armor the plates. Okay, protective shields so that we can protect the planes. Okay, now tell us where to armor it. Okay, and this is the data that we have. Now based on this data, where would you think the armor should go? Okay, now you have to remember that you cannot armor the plane because you want to protect the plane indiscriminately, right? What would you do? Okay, let's say that let us armor the entire plane. What would happen? It increases the weight, right? It compromises on maneuverability, the range it flies reduces, right? Then it can't carry ammunition that it was supposed to carry, etc., etc. So it's a kind of a delicate balance, right? We can't armor the entire plane, but yet we want to armor the plane so that it is safe enough, and then it allows us to do whatever we want to do, right? It is highly maneuverable. It can go it can fly long ranges. It can carry the kind of guns and rockets that we want it to carry, etc., etc., right? So tell us, where do you think would be a good place to armor? Given that we can only armor certain parts of it, we can only say increase the load of the armor by say 1,000 pounds or something like that. Where should that 1,000 pounds of armor go? Okay, by just, close to. I think the rest of the plane is everything else, so it's kind of distributed. But among the 3 important things, engine, fuselage, and fuel system, it seems to be the most hit. Okay, and therefore let us armor that. Okay, okay, so that is the solution. Okay, this is a guy called Abraham Wald who was heading this group, and he was generally considered to be the smartest guy in the room. Okay, and people were thinking about it. And he said that no, put the armor where the bullets are not there. Okay. Why?
Because the plane survived and came back with those bullet holes.
Yes. So the sample is of planes which survived, right? So what that means that, wherever it is not, it is showing that there are no bullet holes. It means that those planes that got hit did not survive, and therefore they are the most vulnerable parts of the plane, right? The ones that got hit in those other places, even fuel 1.73 bullets per square feet or something like that, right? Per some square area, right? Yeah, square foot, right? So in spite of getting so many hits and it still managed to survive means that it is not such a critical area of the plane, right? So which means that fuel tanks can take some bullets and then still manage to survive, right? But it seems that where the bullets are not there, not there at all, because again statistically speaking, there is no reason why a particular part of the plane should not get hit at all, right? So assuming that randomly distributed these bullet holes are, why is that there are certain parts of these planes which returned don't have bullet holes at all? Okay, so that means that those are the vulnerable, because even one bullet in that particular part might have been catastrophic or fatal for that particular plane, right? So this is a very critical insight. Generally, intuitively, a lot of people will generally look at the numbers and say that, oh, that seems to be the most vulnerable, and go for the highest number, right? In this case here, rest of the plane, suppose you discard rest of the plane because it is all of the rest of the planes, when the other things, okay, let us go for fuselage, right? Or fuel system or something like that, right? So the officers saw an opportunity for efficiency. They wanted to put the armor on the plane with the greatest need, where the planes are getting hit the most. Okay, so that's the wrong analysis. But exactly how much more armor to put on those planes, that was the answer they came to Wald for. Okay, they are already decided, in fact, right? Because the army generals are not statistically trained and therefore probably not very good at analytics. So they said that no, we have decided this is where it should go, but then when just want to confirmation or exactly how much do they thought that this group will work out some kind of a system to estimate the amount of armor but then they fundamentally questioned their analysis, right? This group questioned it and said that the armor does not go where the bullet holes are, it goes where the bullet holes aren't. Okay, what is the insight that Wald was hoping to get by asking where are the missing holes, right? So that is a question he asked. Okay, where are the missing holes? Okay, so the error, you can see what they were doing. The planes that came back were a random sample of all planes. They were not a random sample of all planes, right? So if you manage to collect all planes and then create a random sample and then come up with this number, the numbers would have looked very different, right? But because the planes that were completely lost could not be counted at all, so you only had a non-random sample of it, right? You only had a, okay, so this is what is called a survivorship bias. Okay, so for example, if you take some kind of a survey with people who survived cancer and things like that, right, and then find out about some of the things that they did, would be not very conclusive, because your sample is not a sample of everybody who had cancer. Okay, so we'll see a few other examples that will kind of expose this flaw in the way that you analyze or you think. So we have some interesting questions from UCID. One of the questions that I created way back in 2016 UCID was this. Okay, has some similarities to the Wald problem. Okay, so this is a question some of the BDS guys must have come across this question. A recent survey among concert goers found that smaller, older halls sound better for symphony orchestras as compared to bigger modern ones. What are the reasons for this? Okay, smaller halls are better able to reflect bass notes from the side walls and the ceilings, which makes it as an important factor for the quality of the symphony sound. Old halls are part of history and heritage, so people think they sound better. Old concert halls with good acoustics tend to get maintained and preserved. while ones that are suboptimal acoustics get renovated or replaced. The atmosphere is more intimate in older concert halls, visually as well as acoustically, because the concert goers are relatively close to the musicians. Now, what is the correct answer? Okay, so every one of them is correct, right? Because it is asking about the perception of what they think, not based on some kind of a empirical measurement, right? So they asked a bunch of concert goers that, why do you think these heritage concert halls sound better than this very modern new concert hall, right? And then everything is possible, right? They say that, I mean, the first one is technically correct, right? Smaller concert spaces sound better, right? So that's technical reason for it. Heritage, people think that they are better because, I mean, people can think anything, right? Older concert halls, good acoustics tend to get, so that is the survivorship bias that I'm focusing on, right? The very reason that this hall has survived for 80 years, 90 years and still around, still it is maintained as an acoustics hall or a concert hall, tells you that there is some quality that is being maintained here, okay? There is some kind of a sound related value that people are maintaining, or at least they have been constantly upgrading it in order to maintain the kind of sound that they want to have inside the concert hall, okay? Because if it was not, it would have gotten removed or completely renovated into a modern concert hall, okay, which has happened to many concert halls. The atmosphere is more intimate. So the second one and the fourth one are perceptual biases that people have about certain things, older, nostalgic value to it. It has been part of our history and heritage, 50 years, and so whatever sound it happens inside must be good, right? So but it is an undeniable factor, okay? And therefore they think that when you feel and think that it is, you believe that it is better, then I mean, obviously you kind of evaluate the quality of the sound itself, right? So all of them are correct. So there are more examples of similar nature. So the first one is very similar, which is before the introduction of the tin helmets during the First World War, soldiers only had a cloth. You must have seen in old movies that the pith hat, right? A thick pith hat, khaki colored ones, very lightweight, and it is breathable and it's comfortable to wear and all that. That is the whole idea of doing that. But it was during only the First World War they introduced the tin helmet, the metal helmets, right? And it was very, very uncomfortable for people to wear because it was heavy, it was not ergonomically designed, and it was not breathable, so people were like sweating inside, hot climates and so on, okay? But after the introduction of the helmets, the number of injuries to the head increased dramatically, causing the authorities to worry whether we did the right thing or not, okay? So what they expected to see was that now head injuries will not be there because they are better protected, right? But then it turns out that many injured soldiers were coming in with more head injuries than before. Why?
Otherwise they would have died.
Exactly, right? So the pith helmets were not protecting them at all, right? So if you got hit in a bullet, despite wearing a pith helmet, you did not survive. So you did not have a head injury at all because you are dead, right? So the worst thing than being injured is being dead, right? You're counted as dead rather than counted as somebody with a head injury, right? So the data would not have recorded them as, maybe the details of the death would probably say that cause of death would be like head injury, bullet to the head or something like that, right? So if you just look at the data, it would have told you that before tin helmets, no head injuries, after tin helmets only head injuries. Now the tin helmets are supposed to protect head injuries, right? But what is happening here, right? So again, this is a survivorship bias. Study was conducted on 4-year-olds, comparing those who went to preschool and socialized with other children with those that stayed at home with their mothers. It measured the aggressive behavior of such as stealing toys, pushing other children, starting fights. It showed that children who went to preschool were 3 times more likely to be aggressive than those who stayed at home with their mothers, okay? The report was used to persuade parents to keep their children at home, okay? Say that don't send your kids too early to school, because the data suggests that, kids that who stay at home for much longer are less aggressive, right? And they are then the ones that are there and they get into trouble, they become aggressive, they develop all these antisocial elements, habits and all that, right? So this is so they used. So what is the flaw in this reasoning?
Staying at home, they don't get other people to.
Yeah, they don't have anybody to be aggressive with, right? Or to steal from, right? Or to fight with, right? So it's just, you are postponing the inevitable, right? So a follow-up study or a longitudinal study with these same kids over a period of time would have revealed that no, it doesn't matter whether they go at 3 o'clock, when they are 3 or 5 or 7, they would do the same thing whenever they are exposed to that environment, right? It turns out that that's what happened, right? So 3 to 5, don't send the kids to school, be at home, very nice kid, well behaved and all that, and then when he goes to school at 5 o'clock, starts this behavior, right? As opposed to somebody who went at 3, he starts it earlier, that's all. That's the only difference, okay? A study found that a strong correlation between accidental deaths due to drowning and the amount of ice cream sold by street vendors. So what can you conclude with this data? So whenever there is a lot of drowning deaths, those days had the highest ice cream sales. So can we say that one is causing the other or somehow they are related? Are they related at all? Okay. Okay. Why is our higher crowd? Yeah. So it's a seasonal effect, right? So people go out and then swim only on very hot during hot weather, and hot weather is also a good time when a lot of ice creams are sold. Okay. So this is what is called as a some kind of an unrelated thing. Two things are happening because of a third variable that is not part of the data. Okay. So that third variable is independently causing both of them, but these two are not at all related. Okay. So this is what is called as a collider bias, right? Which is that two things you look at it separately and then together, and then you see that there is some kind of a correlation, right? So these are called as spurious correlations, right? And there is a very nice website which actually tracks all these spurious websites. In fact, what they do is they take two graphs and then match these two graphs. They are kind of identical graphs, right? And they are completely unrelated, right? The amount of money that Batman made and then the poverty level of some other country, there is a kind of correlation, right? So and then can we now find some correlation between them? There is nothing, right? They are completely independent of each other. Maybe there is a third variable that is causing both of them, but it could be that there is. So just Google the term spurious correlations, and there is a very nice kind of a bloggy type of a website that posts very interesting such spurious correlation. Most of them are really funny.
So how do you spell it? Spurious.
Spurious, right? Yeah, Spurious. Okay, so this is from a study again. So you just look at it, there is hospitalization, locomotor disease and respiratory disease lead to hospitalization. There seems to be a very high correlation between these two, right? Now people concluded that no, if you are less mobile, then you do not exercise, you cannot exercise, right? Then your lungs become weaker, and then you have you develop respiratory resources. Okay, so this is from a very famous study in 1979. It analyzed data of 257 hospitalized individuals and detected an association between locomotor disease and respiratory disease. Okay. Now look at the sample, right? Hospitalized individuals, right? The association seemed plausible at the time. Okay. Locomotor disease could lead to inactivity, which could lead to respiratory diseases, because you don't exercise, you don't move, you just sit at home all the time, and suddenly you expose yourself to slight bit of vigorous activity like walking or climbing stairs, you will see that you're breathless, right? So it seems very obvious. But when the same guy repeated the analysis in a sample of 2,783 individuals from a general population, he found no association. Okay. The original analysis of hospitalized individuals was biased because both disease caused individuals to be hospitalized, right. But looking only within the stratum of hospitalized individuals, Sackett had observed that a distorted association. Okay. In contrast to the general population, which had a mix of both hospitalized and healthy individuals, you notice that that association disappears. Locomotor disease and respiratory disease are independent causes of hospitalization. Now, that is the correct conclusion. Okay. The collider is the hospitalization part.